position time graphs meant. I reminded you on Friday that we don't want to memorize these. Rather, we want to figure out every time we see one of these graphs what each of these shapes represents. Before we do that again, before we spend a couple of minutes reviewing these shapes, I want to review something else, and that is the positioning of the variables on the graph and the title as well. The first word in the title is always which axis? Good. It's always the y-axis. And the y-axis of the graph, which is the first word in the title, is also always which variable? The manipulated or responding variable? The responding variable. Good. Versus, or as opposed to, the second word in the title, time in this case, which is always on the x-axis of the graph, and is not the responding variable, but rather is the manipulated variable. Good. Now, I've titled this position dash time graphs. You could title it position versus time. That would be okay as well. Position as a function of time would be okay as well. But position has to be listed first. Time has to be listed second because of where they appear on the graph and what type of variable they are. Now, let's take a look at the particular shapes here. When we see a straight line means constant something, right? Constant or uniform something. Just a matter of what it means. Constant or uniform, constant or uniform, constant or uniform. Let's see what each of them mean here, okay? If we have position and time, then it's probably going to relate to which variable? Position and time is going to relate to velocity, somebody said, because velocity is defined as the rate of change of position, how quickly the position changes, basically how much time it takes for the position to change. So the slope of a position time graph is going to be velocity. And if that slope isn't changing, then it must mean it's a uniform or a constant velocity. I don't care whether you tell me on a quiz or a test whether that's uniform or constant velocity. It doesn't really matter. It means the same thing. Now, the second one, that's a straight line as well, right? That means uniform. That means constant. Is it constant velocity, uniform velocity here? Well, it is kind of, right? But it's a very specific uniform velocity. Specifically, it's a uniform velocity of 0. Good. Which means, in other words, that it's not moving. So if you want to just say it's at rest or not moving, that's probably the easiest way of stating that one. Now, this third one's a position time graph with a straight line as well. Straight means uniform or constant, right? Constant or uniform velocity, some speed, velocity, sure. What's the difference between the first one and the third one then? First one is constant or uniform positive velocity, and somebody said back here, Katerina, I think it was. Was it you? No? We have constant or uniform negative velocity in this case. By rights, we probably should have written the positive in right here. But if we don't write it in, it's kind of assumed that it's positive, whereas here it's important to write in that it's negative. You could also think of it as constant or uniform backwards velocity, but I don't want you to think of it as you need to walk backwards or go in reverse in your car. You're just going in the negative direction, right? What's the fourth one? This is where things start changing, right? This is not a straight line, it's a curved line, which means that something's changing. What's changing? No, the acceleration is not changing. The acceleration is not changing. What's changing? What's changing? Yep. The speed of the velocity is changing. In other words, it is accelerating. This is a positive acceleration. But that doesn't mean the acceleration is changing. Okay, the acceleration here is likely, we don't really know for sure when we look at this graph, but it's likely to be a uniform value, a constant value. It's just the speed isn't a constant value. It's speeding up, but the rate at which it speeds up remains the same. What's the fifth one mean? The last one. This is what? Acceleration, did you say? Yeah, you could say negative acceleration. What's another word for negative acceleration? Yeah. Deceleration? Yeah. I'd accept either one of those on a quiz or a test. Negative acceleration or deceleration. Negative acceleration is probably a more precise scientific term, but deceleration works just fine as well. All right. What we're going to spend some time on today is determining variables from specific graphs. Not just determine the shapes, but how do you determine a number from a graph? There's a couple of things specifically that we're going to want to find. The first one would be position. If I want to find the position on a position time graph, good news is it's ridiculously easy. Whenever you want to find something on a something time graph, yeah, you want to find y on a y time graph. You want to find position on a position time graph. You want to find acceleration on an acceleration time graph. You want to find something on a something time graph. You want to find anything on an anything time graph. You want to find something that's on the y-axis, just go up and over. That's it. That includes a position time graph, finding position. So if I want to find the position at 6 seconds, I go over to 6 seconds, I go up and over, bam, there's my position. Easy. That's the easiest thing you can possibly do. That might be the easiest thing in Physics 30. You want to find, sorry, Physics 20. You want to find position on a position time graph, just go up and over, no calculation involved. Now displacement's a little bit harder, because displacement is defined as the, remember this? Displacement is defined as the change in position. So if you want to find displacement, what do you need? 2 positions. So you're going to go up and over, and then you're going to go up and over again, and then you're going to subtract them, yeah. So let's go up and over times 2, then subtract. So if I want to find the displacement between 2 seconds and 6 seconds, let's say, I go up and over, I go up and over, take these 2 positions and subtract them. And you already know how to find the average velocity anytime, right? Average velocity is always what? This is not new. There's your hint. Okay, all of you know the answer to this already. The average velocity is always what? Yep. Be careful. It's not change in displacement, change in position, or just displacement over time. And we already found the displacement, right? We just take this number, whatever we got right here, and sub it in for the displacement divided by time. Finally, the instantaneous velocity. What do you think that means? Instantaneous velocity. Not at the start, not necessarily. Yeah. Okay, but that's not what instantaneous means, but you're on the right track in terms of getting the answer for it. Instantaneous means at one moment, at a specific moment in time. So if I want to find the instantaneous velocity at 4 seconds, or the instantaneous velocity at 6 seconds, whatever. Okay? For now, we're just going to say how to do this if it's a straight line. If it's a straight line, then it's going to be the same as the average. Nick was kind of alluding to that, right? If it's a constant velocity from 0 to 10 seconds and you found that to be 6 meters per second, well, then the instantaneous velocity anywhere along that trip is going to be 6 meters per second, right? If it's not a straight line, it's a curved line, or if there's a couple of different straight lines, then we got to do something else. We'll deal with that. But right now, we'll just do questions involving a straight line. Let's have a look at example number 5 in your example question booklet. This one says, use the following information to answer the next 5 parts of this question. The good news is there's 5 parts of the question, but But they go pretty quickly. It's not like it's 5 really, really long questions. They're 5 short questions. Now this graph is entitled, and by rights it should be. Graphs should always be titled. What would the title of this graph be? Position versus time. Actually, I see it is in yours. It's just not in mine for some reason. It should be position versus time, or position dash time, or position as a function of time, because position is a responding variable on the y-axis, and time is a manipulated variable on the x-axis. Now, there's 5 things we want to find from this. A, first of all, we want to find the position of the object at 10 seconds. Whenever we want to find anything on an anything time graph, including position on a position time graph, what do? 3 words. Up and over. Good. Up and over. So let's go to 10 seconds. 10 seconds here. Let's go up and over. Wow, it's hard to see from being this close here. Go up and over. Ideally, you're using a straight edge here. I'm just going to take a look at my original because it's a little bit easier to see it here. Looks to be, whoa, careful here. How much do my intervals go up by? It's going up by 4, right? 24, 28, 32, 36, 40. This is going to be 30, isn't it? The position here is 30 meters. I'll define east as positive, so everything we get here is positive. We could say 30 meters east, or we could just say positive 30. Either one of those would work. The displacement between 0 and 10 seconds. The displacement is up and over times 2. In other words, it's final minus initial position. The final position at 10 seconds, we already know, is 30 meters. What's the initial position at 0 seconds? 0 seconds, we go up to 80 meters. So let's say 30 minus 80 meters. Gives me what? I get negative 50 meters. I said negative 50 meters, which is the same thing as saying 50 meters to the west. If I define east as positive, then that's fine, though. The average velocity between 0 and 10 seconds. The average velocity between 0 and 10 seconds. What's that? How do you find average velocity? We've done that now for days, just not in this context. Average velocity is always, yeah? Good, displacement over time. And the displacement, we just found, it's negative 50 meters. Divided by my time is 10 seconds. That's going to give me negative 5.0 meters per second. Now, some of you might be thinking, well, man, if I made a mistake in question B, I'm going to get C wrong for sure, right? Yeah, you are. The good news is, if this was a quiz or a test, and you got B wrong, but did C correctly with the wrong number, I'd still give you the marks for that. So you'd still get 100% on C, even if it was wrong, as long as it was consistent. In other words, as long as you did it correctly. You're not going to get penalized twice for one mistake. Right? You'll get penalized once for one mistake. The instantaneous velocity at 2 seconds. What do we know about the velocity in this graph? It's a straight line, right? So what do we know about it? It's constant. Yeah, it's not changing. Somebody said. It's not changing. If it's not changing, and the average is negative 5, then what's the instantaneous velocity at 2 seconds? Negative 5. If it's not changing, and the average is negative 5, then the velocity at 2 seconds must be negative 5. What about at 7 seconds? If it's not changing, and the average is negative 5, then the instantaneous has got to be, Miguel? Same thing, negative 5. If we have a straight line graph, and we find the average velocity, the instantaneous will be the same everywhere. Now, if you don't have a straight line graph, all bets are off there, but that's not going to happen yet for us. I'd like you to take a look at worksheet number 3 now. Worksheet number 3. There's a few questions on this worksheet, but for now, I only want you to do, well, this sounds bad. I only want you to do the first 10 questions. which is really just relates to the first two graphs. Okay, does that make sense? So questions 1 through 10. Now, notice a couple things here. First of all, in this graph, question number 1, well, questions 1 through 6, you have your direction is west. What I would do is define west as positive there. Does that make sense? You could define west as negative, but since it's above the x-axis in your graph, I'd probably make it positive, since everything is west here. Does that make sense? The second thing is, you notice you have two straight lines. So just watch that. Two straight lines. That means the average velocity for this will be the instantaneous velocity anywhere along here. The average velocity for this, the whole thing, will not correspond to the instantaneous velocity. Does that make sense? Okay, take a look at the first two questions, 1 and 2, and after you've done those, we'll take a look at them. Let's have a look at the first 6 questions here that go with the first graph. Number 1 says, determine the position of the object at 7 seconds. So what we're going to do for position on a position time graph is the same thing we do for velocity on a velocity time graph, or momentum on a momentum time graph, or force on a force time graph, is go up and over. So at 7 seconds, yeah, it's really hard to see this on the board from where I am here. At 7 seconds, this is 6.4, 6.8, 7 seconds right here. We go up and over. At 7 seconds, it's 30 meters. Now, I'm going to define west as positive here so that I don't have to worry about the negatives there, right? Negatives on a graph here, like especially when it's above the x-axis, it gets confusing. So just whatever's above the x-axis, east or west, make it positive. What's the displacement between 0 and 5 seconds? Well, at 0 seconds, right, the displacement is final minus initial position, which is up and over again, and then subtract them. My final position at 5 seconds, this is 4, 4.4, 4.8, 5 seconds, up and over. My final position is 30 meters. My initial position at 0 seconds is 0. So 30 minus 0 is 30 meters. Now my average velocity between 0 and 5 seconds, what do I do for average velocity? Done it a million times. Not a million. We haven't done it a million times, but several times. Yeah. Yeah, it's just displacement over time. And we just found the displacement is 30 meters. Now, a lot of people were asking me about this. I wasn't anticipating this question, but a lot of people asked me, so clearly there was a little bit of an issue with it here. How do we find the time? Well, the time interval between 0 and 5 seconds is 5 seconds. The time interval between 1 and 5 seconds would be 4. The time interval between 10 and 14 would be 4 seconds, right? We just subtract the 2 times. So my time interval here is 5 seconds. 30 divided by 5 seconds is 6.0 meters per second. And the average velocity between 0 and 9 seconds. Well, the displacement between 0 and 9 seconds, at 9 seconds, the position is 30 again. At 0 seconds, it's 0. Over 9, 30 divided by 9 is that 3.3? Look, my average velocity went down, right? It was 6 meters per second. When we look at the whole trip, it's only 3.3. Well, that's because the last part of the trip I was stopped, right? It was a horizontal line, it was at rest. And when it stopped, that's going to decrease your average velocity, right? Just like when you're driving to Edmonton and you stop in Red Deer for half an hour for lunch, it decreases your overall average velocity. Now, 5 is a little tricky. The instantaneous velocity at 3 seconds. What's the velocity right here? right here. I can tell you right now, do not go up and over. The other tricky thing about this is that we said the instantaneous velocity is the same as the average when it's a straight line. There's two straight lines here. But we already know the average velocity of the first straight line from question number 3 was 6 meters per second. Right? Not the overall average velocity, but the average velocity of that straight line was 6, right? So what's the instantaneous velocity right here? What is it here? What is it here? Here. Here. Over here. Not 6. Right? We'll worry about what it is later, but it's not 6. Along that straight line, it's 6 meters per second everywhere. That includes for question number 5. At 3 seconds, it's 6 meters per second. Same as it is from question number 3, right? And finally, 6, determine the instantaneous velocity at 8 seconds. At 8 seconds, it's a different straight line. This straight line represents an object that is, it's now stopped. Okay, what's the average velocity in that interval? Okay, well, what's the instantaneous velocity anywhere along that interval? Here. What is the instantaneous velocity here? What is it here? Here. 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 It's 0 everywhere there, right? So the instantaneous velocity there is going to be 0 meters per second. All right, let's finish up 7 through 10 tonight. If you haven't already finished it up, you can stick around for scheduled help and ask me questions on it if you want. If not, we'll see you tomorrow.